Hello everybody and welcome to class. I actually didn't realize the counter was done. I was writing in the email. I was just about to hit send and I'm like, oh snap, the counter is done. So welcome to class everybody. Let me hit send on this email and I'll be ready to go. I have class, I'll write later. Okay, cool. So yay. Actually, so guess what? So the email was related to the cheating stuff. So it turns out that using services like check is actually a misdemeanor in Nevada. I did not realize that until yesterday. Nevada NRS 207.230, I think, states that if you pay somebody for a solution, which can be alluded to, including subscription services, that you then basically submit as your own, is actually a crime in Nevada. So that's actually pretty interesting. So I'm gonna have to modify the academic content video and include that, since it sounds scary enough to include it. So I don't know how actively they prosecute such a thing. You know, I've never actually read in the news of somebody going to jail for cheating, but I'm going to assume that it's there to support copyright infringement as well. So I don't know. You know, people don't go to jail for putting videos on YouTube of music. So I'm assuming that they don't actively prosecute. But still, it sounds scary enough to put. And in theory, maybe if it's so bad, they would prosecute it. So, anyways, okay. So anyway, so today we are going to be talking about a couple of things to wrap up our pointer stuff and memory allocation, and that's going to be, we're going to make that 3D array, since last time we made a 2D array, so now we're going to make a 3D one. Then we're going to talk about copying arrays, because you will find out that something quite interesting happens when you try to copy something like an array. And you probably saw this in actually even 135 if you try to make a copy of an array. So we're going to talk about the concept of deep and shallow copy and how to solve this issue that we're going to run into. And then finally, we're going to go back to object-oriented programming and talk about constructors and destructors again. This time, though, we're going to finally be able to find a good usage to destructors, which is going to be with dynamic memory allocation, because that's the best place to do your de-allocating, actually. So that is the schedule for today, which I think we will basically cover all of this before the end of the class. Then we can start talking about virtual functions, if such is the case. If not, then we will talk about that tomorrow. So that is the plan. And don't forget, your exam is on Thursday. So today will be the cutoff. Assuming we finish all the stuff that I have listed here, it'll be the cutoff of the test. And in the case that we don't, for some reason, finish these 3 topics today, then I guess the cutoff will be tomorrow. But I highly doubt it. We should be able to get through this. So, without further ado, let us open the code from last class. And so here was the code that we did for a 2-dimensional array. First, we have to create the outer row. I guess maybe as a refresher, let's go ahead and look at this picture. So what we're trying to do is this, right? A 2D array basically has a row and a column number. Here we have 3 rows and 4 columns for a total of 12 items. And it turns out that when you're doing things dynamically, what you have to do is first allocate one dimension of it and then the second dimension. And that first dimension doesn't actually hold any data. All it holds are pointers. It holds 3 pointers that point to individual 1D arrays, because your main memory and in general any sort of dynamic allocation can only be kept as a single dimension. So the way you get around that is by making basically pointers that point to each of these columns. And so here we have the first, second, and third pointer, each pointing to a horizontal array of size 4 that is basically the representation of a column from this. And so we can basically achieve it this way. And while this is kind of weird, it actually turns out that it's very intuitive when you're actually accessing the members, because you use your square brackets like you've done before, and you don't have to do any weird stuff. So that's good, because this is what we're familiar with when we were making 2D arrays the old way, when they're static, they're not dynamic. So that's essentially what we did last time, and you can see here that we are making a double pointer, although that's not technically the right name for it. It's a pointer to a pointer, and that is because in the drawing that we have here, ARR is up here, and that is actually a pointer that is pointing to the first element of the array. So really, the only thing here that we keep in the stack that is at compile time is the pointer R. Both the array of pointers and then the actual arrays that contain the data are stored on the heap and are dynamically allocated. And so that's something important to realize, that that's the only one that you have to really allocate at compile, when the program starts, basically, which you have to set up at compile time. So because it's a pointer that's basically just pointing to another pointer, then it's a pointer to a pointer, right? So think about it this way. The little asterisk here, that one is there, and then that one is there. It's a pointer that is pointing to another pointer, okay? So hopefully that makes it easier to understand, but that's why there's two asterisks there. So first we have to make that dynamically allocated array of pointers. So that's exactly what we're doing here. We are setting the address of whatever this is pointing to basically point to the first element in the array of pointers. And the way that we make an array of pointers is we use the new keyword, and then we use the type of the element is going to be pointers, because again, it's an array of pointers, and not just any kind of pointers, they're integer pointers, because that's what we're working with. And so because of that, we say int star. That means that this is not just if it was a normal array like this, then you would just say int and then the size. Here we're saying int star. That means it's pointers, right? Not just any type of variable, it's a pointer variable. And then we basically specify the size. Of course, here we hard-coded the sizes. If that was really the case, then I would find no reason as to why we would want to make this dynamic. But of course, we could do a cin or read in from command line arguments these dimensions, and then that's when you need it at runtime. For now, I just hard-coded them here just to make the assignment, the example faster to run, so I don't have to manually type in sizes. But that would be the idea, that you would want to make these variables that basically read in from external input, whether that is a terminal or a file, and then make your array. So when you're making assignment 5, which is basically the remake of assignment 1, it's you're basically getting rid of all the vector stuff with the Twitter data, and then you are making dynamically allocated arrays to store all the tweets. And how big are you going to make them is going to depend on how many tweets you have and how much data they have. And so what you need to do is you need to first count how many tweets you have, and then actually read them in. That way you can make the array the correct size and not bigger or smaller. So anyways, back to this. Once we go ahead and make the array of pointers, now it turns the time to make the actual arrays that hold the data. And because we need 3 of them, and that happens to be the size of the pointer array, we can just do that in a loop. And so that's exactly what we are doing here. Going for each of the rows, each of those pointers are going to point to a column. To an array of the size of column, which is 4. So that is what is happening here. And then this is me just printing it afterwards, so you can see what's there. Of course, this is merely a pointer. It's not really holding any information. So actually, what did that? The prop print as an address, actually. So, all right, it's not the right one. C++, dynamic array. Here we go. So these are the 3 addresses that that's actually printing out. So that's what that line is doing. From there, we went ahead and actually filled in the array. As you can see, we were able to access it very comfortably with those square brackets. And we just filled it in with random numbers. That's what this is. We're just basically counting the spot that we are in the loop. That's why they're going up like that, and then they go down and like that. So just to fill it with random stuff. Of course, you want to fill it with useful stuff if you're actually doing this for a reason. Finally, comes time to de-allocate. actually, well, this loop just sets them, and then this loop just prints them out. When it comes down to the allocate, we gotta work our way from the inside out. Whereas when we were first making the array, we worked our way from the outside in, because we started out making pointer, then making the array of pointers, and then finally making the arrays of the actual data. We're gonna work our way backwards for the allocating, which means we're gonna first get rid of the arrays of the data, then of the array of the pointers, and finally we're gonna set to null the AR pointer, that pointer to pointer. And the way we achieve that is going to be with a, scroll that down, a loop, because we want to get rid of the three basically arrays of data. And so that is going to run for the number of rows. And because this is not just a single integer, but an array of them, we use this delete with the square brackets in front like that. And that signifies the computer to actually go in and delete the data of an entire array. Not by delete, by the way, we are talking about de-allocation, which is very different than deleting in the sense of the word delete when you talk in English. The allocation merely releases that memory. It doesn't necessarily clear out the contents of the memory. Furthermore, you still have access to these things via the pointers and the array of pointers, so therefore they are dangling pointers at this time. Okay? However, we're not going to set them to null because, well, I'll tell you in a second. Let me finish this first. But right now we technically have that issue. This is a dangling pointer because we can still access the data inside. So next we're going to go ahead and deallocate the array of pointers. And yet again, we use the square brackets here with the delete because this is an array. And yet again, this is technically a dangling pointer because while we have deallocated those three pointers in that array, they still contain the address of our columns. So you can say we have almost like a double dangling pointer because everything is still accessible by R. That initial pointer that points to the first pointer of the array of pointers, that still is existing with the address that we currently have stored in the array of pointers, even though they're no longer ours. So we can technically dereference both the array, the R pointer, and then the array of pointers, anyone there we can dereference and actually get to the data. So we can access all these dangling pointers. So your initial sort of solution to this might be to just keep setting things to null as you go. So for example, after you go ahead and delete this, you might want to set each of these R's to null. And then you may also want to set R to null here like I did. However, it turns out that it's not necessary to set each of the individual pointers here to null. You can just set R to null and basically solve your problem. Here's why. Let's kind of redraw that picture down here. You can see that. So right now, you know, this is your computer trying to access dangling pointers, right? And right now you have R, and R has a pointer pointing to the first element here. And then technically you can access any of these by basically doing +4 +8, right? And then these pointers are all pointing to the actual contents of the data, right? And so when you free things, you're not cutting any links off, right? So your initial thing might be, well, then just cut these links away, right? And then maybe also cut this link away, right? That would work. However, if I just cut this link away, and then I don't technically need to do anything to the bottom links because I can't even get here anymore. You know, once I cut this link here, that's the important one because I basically cut the supply chain or whatever. So there is no way for me to get into the array of pointers. And because there's no way for me to get there, then there's no way for me to get from there to the actual data. So it turns out that when you're trying to solve dangling pointers, you don't need to just keep setting every single pointer to null. Just set the one that actually would break the link to everything else. This is actually kind of useful when you're talking about like a linked list at the end of the summer session when you really only gotta cut the head of the snake per se, you know, or the linked list. You don't need to cut each individual link, okay? Because again, you know can see this guy. You cannot see these or these because they're in the heap and you don't have an access to them. So all you gotta do is set basically this one to null. And null means basically just, you know, cut this link away. And now, because this is null, you have nowhere to go here. There's no way for you to get here or here, okay? So that's essentially what I mean when I'm talking about just having one null instead of 4 potentially. Okay, so going back to the code, I achieved that with a single null right there. Okay. Would this create any type of security issue? Is there a way the data could be retrieved? The only way, okay. This would be what you would consider as security through obscurity, which means you basically cut the way. As whether you're actually doing this to make something secure, I'm here to tell you that that's not secure at all. You can look around the addresses and possibly find it, but then again, you're not trying to do something that is secure. You're merely trying to make something that is secure in the sense that you're trying to make something that is not accidentally broken, you know? So it's the same thing with private variables that I said. The private variables are there to prevent programmers from accessing stuff they shouldn't. However, it's an honest man's thing, whereas like someone with a good, that's not trying to do something malicious is not going to access it by accident. However, as I showed you very quickly, and we'll come back to that again, it's very easy to access private variables if your intentions are they're like malicious intentions, right? So private variables and setting null as a way to avoid dangling pointers are by no means something that I would consider like cyber secure. They're just protections to prevent people from doing things they shouldn't when they're not having malicious intentions. So it's basically to prevent what I would consider a dumb mistake versus actually trying to make something secure from hackers. No, you're not. It won't help you. That's not something that you're really trying to do because, you are. I would have to get to ways to sidetrack to talk about security, but yeah, again, you're not trying to make this secure at all, and you don't have to actually. It's just merely again to prevent accidents from happening, and that accident is basically accessing a dangling pointer. Of course, in the real sense, if you wanted to delete some information, the best thing to do and the most basic thing to do is to overwrite that information. So if for some reason you really just wanted to hide that information, suppose you made a static array, you can't really get rid of that static array. It's there forever. But if you want to really delete it, just overwrite it. And that's actually pretty secure, actually, if you really think about it. When you overwrite something, that information is gone. Of course, to be extra safe, you can overwrite it a couple of times. But yet again, actually, there's a potential risk that information doesn't propagate to the hard drive immediately. So yeah. Anyways, like I said, I don't know. This goes way to the side. I guess this is the time to pitch that I am teaching a cybersecurity course next spring. It is a graduate level course though, so I don't know if you guys can enroll in that. But if we're still online, then I guess I'll make it public on YouTube. If not, then I'll record it and put it on YouTube. Yeah, it's part of the new master's program for cybersecurity that just got approved. So yeah, that'll be an interesting class. Although actually, the one that I'm teaching is very basic. Think about it; it's like the first class. So yeah. Anyways, probably talk about this then. Let's go ahead now that you hopefully refresh your mind from last class and expand this concept into a 3-dimensional array. Okay, so we're going 3D, guys. So how does that look if you want to actually draw what a 3D array looks like? It's going to look like something with depth, right? Like a cube or a cylinder, I suppose, to make that to us, but that'd be weird. Hang on, gotta take my watch off. It's messing with my art. There we go. Close enough. Yeah, good enough. Okay, so suppose that we still have our 3x4, but now we added a depth to it, and that depth is going to be let's just go with 2 for now. Okay, so question for you guys, because I have the dimensions 3 by 4 by 2. How many items, and let's say they're all integers, how many integers can I store in this 3D array? You guys tell me. Dog is leaving, by the way. Bye, dog. 24. Very correct. Yes. The way you get that is you basically multiply all the dimensions together. Or you can also think of that as slices, right? So we got the first slice in the front, that is our 3 by 4. And then we got 2 of those. So basically, you could kind of separate that. So it's basically behind it, so you kind of put it at the side so you can more easily see it, right? So typically when we go to higher dimensions, the easiest way to sort of view it is to just kind of flatten it out by splitting it. Now, if we went to 4 dimensions, technically, you know, you could just basically do the same thing. You could put two squares inside, you know, so that you don't have to draw a hypercube. So, okay, good. That's kind of what we're going to be doing in with the pointer stuff. We're also flattening things out because there we can only have 1 dimension. So turns out that how we are going to be able to implement this is we are going to have still, okay, that's interesting. We are going to have still our, yeah, of course, I have to decide how we're doing the dimensions, but we're going to do the dimensions like 3 by 2 by 4. Actually, no. Let's go ahead and do 2 by 3 by 4 because that looks prettier. And it'll actually kind of match what we're trying to do. So what we're going to do is we are going to basically take, interesting line behind me, but okay. Oh, whatever, it's a special effect, whatever. Okay. So we are going to make an array of pointers of size 2. That's going to represent our depth, okay? And each of those are going to point to another array of pointers. Here, I'm going to put this one down here so I have space. And again, when I say point, they always point to the first item in that array. And the little asterisk in my drawing represents that it's a pointer variable. Okay. If it's just an empty square, it represents it's a regular variable, like an integer variable. So yeah, we make those point to pointers, basically a pointer pointing to pointers, like that. And of course, this whole thing needs to be started out by our initial variable in the stack, which is just a pointer. Like that. If it makes you feel better, this is technically a triple, and then these are doubles now, like that. So I can do that if you want to. So you can better appreciate what the level of complexity with this. And then finally, these arrays of pointers are going to each point two arrays of size 4. Maybe I should have just drawn one and copy pasted. Apologies. Okay, and so these are actually data, so they don't have a star in it. And as you can see, that's pretty much the same thing we have here, just separated even further into what is essentially little rectangles. Okay, so that's like taking this guy and separating it. Like such. Does this make sense? You guys get this? That's basically what we did. We separated it even further. And because there's 24 of them, you know, there's basically 2 layers of that, so each of the layers has 3. If you count this, 4 times 6 is indeed 24. So that's how we represent our 3D array, because again, we can only have one-dimensional arrays in C++, because memory is one-dimensional. And so the way we're doing it is we're basically, you know, flattening this out into 1 dimension. Just so you can see, each of these are all 1 dimensions each. You either, this thing is technically just a single value, but then this is an array right here. This is an array, this is an array, this is an array. They're all 1 dimension. Everything is 1 dimension, but we are able to keep 3 dimensions in there. And as you can see, whenever you have a pointer pointing to another pointer, you have to add an extra asterisk. So we kind of start out with the final layer of pointers, which is this one, has 1 asterisk because it's just a pointer. But this guy is pointing to a pointer, so that way it has 2 asterisks. But even better is this one up here who has 3 because it's pointing to a pointer who's pointing to a pointer who's pointing to data. So again, it's a little bit misleading to call it a triple pointer, but that's really what it is. It's a pointer pointing to a pointer, pointing. It's a pointer pointing to a pointer that points to a pointer. Yes, there we go. We have to say it 3 times because there's 3 asterisks. So, make sense, guys? The same thing that we did with the 2D array, where we took it higher. Now, suppose that, yeah, just even though we're not going to do it in C++, just to show you, because I think this will help. Suppose that we wanted to make this a 4D array. In that case, we're going to need more space, right? And our flux capacitors to time travel. Let's say that our 3D array happened to be the 4th dimension was 3. So we have a 3 by 2 by 3 by 4. That means that we have 3 of those cubes, okay? That's the past, present, and future, okay? And so what turns out to happen here is this itself is basically an array. Let's make that a little bit bigger. And of course, you will need one more layer here, which has 4 asterisks in it. Now that is an Avengers level threat, guys, which points to the first one. So let's say this is the first one. Okay, so that will be a 4D array of the following dimensions, which would be basically, well, why not? Let's try this. I mean, I'm gonna just draw a little hypercube so you see what that looks like. It would be a little cube with a cube inside of it. Okay? Close enough. Actually, I don't like the top of that. Okay, there we go, and then connect these. Right there, right there, right there, right there. And you can't see it here, but there's a connection right there, okay? So that would be a hypercube. So that would be a 4-dimensional cube, which, to make it better in our measly three-dimensional world, basically, because we can't see that fourth dimension because we're not time travelers, we would just basically flatten it, actually, in a real world, you know? We would basically do just that. So we're actually using the technique that we have to do for flattening. We have to use now ourselves as humans because we can't see into the future or into the past unless we basically flatten it out and say this is the present, this is the past, and this is the future, right? So past, present, future, magnets, how do they work? So yeah, okay? So that's kind of what we have here now. But it does have uses, you know. Sometimes for the arrays could be useful when you're storing data in a specific hierarchy. But now, this one I'm just gonna show you for fun, but let's actually code a 3D array, which will be this one, okay? But you will see, hopefully from the 2D array, when I do the 3D array, you will see the pattern and see that it's quite trivial at that point to make it a 4D array. You just basically add more asterisks and another for loop and call it a day. So, yeah. Okay. Let's get warmed up for coding, guys. It's probably, you know, I have good confidence in my abilities, but I still think that we're going to segmentation fault at some point. Just the nature of the monster here. Let's make it in a different file, actually, because we'll copy and paste from this file, but 3D array.cpp. Okay, so we're gonna start out by just copying and pasting our 2D array. Oh, look at that, slags. Okay, there, okay. And now we are going to add a second, another variable here to the rows and columns and call that one def, right? That sounds like a good thing. And we said we're gonna make the exact same one, so this will be def equals to 2. Right, so exact same one that I drew, okay? Next, because it's a 3D array, again, we got asterisk there. And now here, where we're making this array, which this is the outermost array. So here, actually, let me go ahead and switch over to the coding and iPad category. Remember we made that thing? Yeah, nice. So here, actually, the small picture might come in more useful here because it's already shrunk. Yeah. So actually, take this here and just put it somewhere. Maybe just down here for now. Okay, so there's our 3D array that we're making, and that way it's there you go. That looks cool. It's a good reference. So we're making that the whole idea of color coding it was so I could color the colors right now, but I just realized I have like 3 shades of purple or pink or whatever that is. So, okay, the brown. We'll start with the brown. Okay, so the brown up here, that one is going to be this one. So you can see the 3 asterisks now instead of 2. Now this here is going to be the outer pink slash, what is that, like a yellow? It's a like a pea color yellow. And then you also have the red, which looks more pink than red, but it's reddish. So that little thing, the 2 right here, all right, I could almost point to it, but I can't. Right there, you know, this one here. This right here, yeah, I'll just do that. I don't even know what malware stands for, but yeah. That one is going to be the depth. So that is a 2 tier of asterisk because, again, it's a pointer pointing to another pointer. So then this gets basically upgraded to another asterisk. As you see, we're basically going to be adding an extra asterisk to just about everything. And then finally, when we're there, we can go ahead and start making in fact, actually, we'll keep it like that because we'll use that. Let's go ahead and first make that outer array since that's a new one. So that's AR equals new int asterisk depth, right? Because it's the size of 2. Now, when we're trying to make the individual arrays that are size 3, so these ones, those we no longer just want to make one of them. We actually want to make 2 of them. So we will put this in the for loop. That was weird accent. this will go twice because the size of the def. So now we're going to move that inside the array, and we're going to switch this from rows to depth. And then this needs 2 asterisks. Okay? So here we are. Oh wait, no. See, 1 asterisk, not 2. It's not deleting the asterisk. There we go. Okay, 1 asterisk, because this is making the 2 arrays that are these ones here. Those. Okay. No, now I can't even delete it. Shoot. Let's extract the color. There we go. Almost. Good enough. Okay. So, yeah. Basically, that is making that a level here. Okay. And then from there, we actually... oh, yeah. Right. We have to make an I here now. Okay? Because that is going to not set this our pointer, but we want the array that we just made. Furthermore, this is the part where it's kind of nasty. I think that we don't need an asterisk in there, but we might. We'll find out soon enough. Also, let's make this into a nested for loop now, because actually no, we don't technically need to, so we won't. Okay, yeah. No, but then we need another for loop outside here, so we might as well make it nested. That way I don't have to do extra work. So yeah. Okay, so now the problem here is we have a lot of letters I, so let's make this a J. I should just, I have a solution to this somewhere. I could look at it, but no, it's better to code it and paint it, share the pain with you guys. So yeah, okay. I would just use a vector, but hey, you're learning this, so might as well use this. So I equals 0, I is less than depth, r int depth j. Okay, I don't know where that came from. Oh, I see why. No, I don't see why. Okay, so now this is going to run twice, and that is going to make each of the vertical ones, the ones that go all the way down there, the pinkish one. And then we're going to populate that by filling it up with so that means it has to be ij. So we have to fill each of those up with the individual ones that are right here. So I wish we could label this. So let me label these so it makes sense. So this will be, we'll call this A, and we'll call this B, and I guess we'll call this what's before A. Okay, we'll call that A then, and then we'll call this B, and then we'll call this C. So really, in that sense, we have A, B, no, hold on, back up here. This is A, this is B, and this is C, okay? Yes. So that's when we're creating them. That's what we're doing, okay? And I suppose this is also a B and a C here. So because that's A, that's why you have the 2 asterisks there, okay? And then this is the B, so you have 1 asterisk. And then the C does not have any asterisks, okay? So that's what I wanted to get to, so you don't get that mixed up, all right? Like I did. So now, whoa, things look blurry for a second. Internally, we got to run the number of rows that we have. That's going to be the 3. And so that is going to, for each of those, we are going to make an array of size 4, which is columns. And then let's go ahead and, if you still want to print out the addresses, you know, why not? Let's print out the addresses so you can see them. So let's go ahead and print out the address of ARI here. And then let's go ahead and print out the address of ARIJ here. Like such. Okay, so these are all addresses. In fact, we'll put a little label down. Address of B's. And then let's just copy this here, and then these are C's. And then let's do the same thing for A. Like such. Well, there's just one A, so I'll just say address of A. But if it was a 4D array, then you'd have an array of these as well. Okay? So there we go. We just declared our array. We have dynamically allocated our array. That was easy. I think, yeah, that's it. Cool. Okay, so now let's go ahead and fill it up with random stuff. To do that, we are going to have to change our for loop here and add another for loop. And k is equal to 0, k is less than, and then we're gonna have to fix that. I could not fix it, but then it'd be weird to access the depth at the end. I'd rather not. So rows and call. We don't need no curly brackets. Okay. All right. Oh man, they're gonna be double digit sized. Well, if they're gonna be double digit sized, then let's go ahead and make sure they're all double digit sized. So plus 10. That way the formatting looks nice. Okay. Now let's go ahead and run another for loop to print them out. So for that one, I'm gonna just copy and paste that one. Oh, and don't forget your k dimension here. And then for printing it out, so it looks cool, we have a couple of options. But again, we don't really have a way of printing it out, at least in the terminal directly, with depth. You know, like that'd be some interesting ASCII art. So we'll just print out the two square side by side option. So like the one where we basically put the two squares like this side by side, compressed together. Okay. So that's what we're going to go ahead and do. So for that, here we just put a space in the first dimension, and then we put an end line for the second dimension. So I guess we don't need these then. But this one we do. Why is it complaining about that? It shouldn't. But okay. Ah, that's why. Okay, yeah. All right. And then we need to put another end line inside of this for loop. Like such. Although here, instead of printing them side by side, because that's way too much work, like logically, we'll just put them one on top of each other. Yeah. Otherwise, like, we have to do some interesting logic here to get that printed out correctly. Okay? Shouldn't line 14 be int rows instead of depth again? Yes, that's a good catch. Because these are the rows. You're right. Good catch. See? I would have sec faulted. Yeah, I would have sec faulted because the depth is size 2 and the rows is size 3. And so it would have sec faulted when I went to the third line. Or if we got to go with it, we have some nasty, not okay out of bounds errors. So good catch on that one. So, okay. So let's not worry about deleting yet right now until we see that the thing works. So for now, let's just comment out the remainder of the delete code, because right now we have done this correctly now that we actually fixed that bug. So, yep. Or I think we did. We have an error compiling that we forgot a curly brace somewhere. Did we now? Oh, I see why. Yeah, this one. Okay. Okay, so let's go ahead and actually switch over to the to that, so we can get rid of that. And then, are you guys ready to see? Ooh, it worked, and then we didn't sec fault. But then again, that's because you guys did catch that roast thing was wrong. So I would have, in theory, sec faulted. I wasn't wrong in that. In fact, let's just see if I would have sec faulted it, or if I would have gotten away with it. It's really depending on the system here. I would have definitely crashed if I tried to delete something I hadn't allocated. But see, I would have gotten away with it actually. However, it's bad. It's bad because I'm accessing memory I shouldn't. In fact, I think Balgrind would have told me of the crime that I was doing. Let's see. Right now, Balgrind should just tell me that there's memory leaks and just kind of call it a day there. So I got a bunch of memory leaks, but I got no errors. However, if I switch this to depth, which is one smaller than it should be, so that means that I'm technically smashing stuff when I'm doing the for loop here. This one will give me 20 errors. So technically just one error. As you can see, one line of code, it's giving me 20 errors. And the errors are basically saying, if we go to the first one, invalid write size of 8. Address is 0 bytes after a block of size 16. That's basically, it's missing that last column that it needed. So, yes, as you can see, you guys indeed were very sharp at catching the LHB rows. That makes me proud that you guys are getting this more. So, good, good, good. However, of course, we gotta still fix those memory leaks, right? So, let's talk about de-allocating this thing. So if we go back to the picture here, the way we're gonna delete this monster is we are going to start from the inside out. So we're gonna first, these, you know, they're dynamically allocated arrays that we just call delete on. So that's gonna be a delete call to get rid of these. And of course, we have 3 of these, so we're gonna put that in the for loop. Actually, we have 6 of them. So ideally, it would be nice if we could get rid of all of them, but at once. Will we be able to do that? I think we should be able to do that. Yeah, we will do that. So we get rid of all these at once, and then we'll get rid of these 2. Then we'll get rid of these, and then we'll just basically sever the link here with a null to avoid dangling pointers. Okay? So that's the plan. So to do that, we are going to need 2 loops. Basically, the same number of loops you needed to allocate, you're going to need to de-allocate. So while we need 3 loops to access data, we only need 2 to allocate and de-allocate. Okay? And you need the outer 2 loops, not the inner one. So you're not going to have to deal with columns at all. And so here we got our loops, and what we have to do is we have to, I should just leave that, actually comment it out. It's called delete on the innermost array, which is C. So that would be ARIJ, no K in there, basically like that. And that's going to basically run 6 times. And it's going to run 3 times here for basically one of the group of trees, and then the other 3 times for the other group of trees. Okay, so that takes care of deleting the C's, right? So I'll put even a C here. But now we got to delete the B's. So for the B's, I can do that in here already, because that way it's going to be okay in the order that things go. So that I can say delete RI, and that'll take care of deleting the 2 B's. Like such. So I don't need this. Okay. Finally, we have to delete the first array that we did. So that one is outside of the loop, because that's just one of them. It's always just going to be one of them, that last layer. So that's just going to be R, like that. And last thing we have to do is going to be to set R to null so that we can cut the link. And there you have it. So let's squish everything together so you can maybe see it all on the same screen. Here, let me put this here. There we go. Oh no, you can't. Can I delete any more curly braces anywhere? And the answer to that is no. So it's okay. We can put that together in the same line, and then we can get rid of this space. Although I really like that space there. So close enough. You can see just about almost everything. Okay. You're just missing the declaration of the def variable. What should you see it there? So yeah, main starts right there. Okay, and there's your return 0. So yeah, there you go. You can pretty much see everything on that one. Okay. Let's see if it works. See if Valgrind. I mean, we saw it work before, but let's see if A, we don't crash, and B, we actually successfully managed to deallocate the memory. And we have victory. We have 0, 0, 0. This, of course, is again because this is coming from the cout thing. I think in the newer version of Valgrind they fixed that. I just haven't updated. And then 0 errors from 0 context. And here is our array. Let's actually take a look at the output here. So address of A, that is the address of the pointers. Maybe we can. Yeah, perfect. Oh, this looks amazing. Yeah, this will be the screenshot for the video. So yeah, okay. So here we got the array A, as you can see there. That is a specific address that happens to be quite separate from these guys. Like there's a big gap in between. You see that? Yeah. So then we have the B's. The B's are kind of close together, but at the same time, not really. Actually, no, they're not. They're actually kind of, they're actually in the same, I'm looking at it. Yeah, they're all in the order that they appear, actually. What's interesting is like what is in between these things, and because these spaces are bigger than what they're actually storing. So maybe it's just spacing things out, and maybe it's doing that to avoid you breaking things. I'm not sure actually, but yeah. So you can see it's allocating an A, only one A. It's doing 2 B's because we have 2 of them, and it's doing 6 C's because we have 6 of them. These 3 belong to this guy, and then these 3 belong to this B. Okay, and then if you actually want to see what it looks like, we can see here's one layer, and here's 2 layers. Second layer, sorry, because it's a 2 by 3 by 4. Okay, as you can see, this gets pretty complicated, and if we go to 4 dimensions, then it gets even more complicated. But at the same time, it's not complicated in the sense that it's difficult. It's a very clear pattern, because look at this compared to this one for a 2D array. All we really did is added another layer of for loops, and then just make sure we keep track of the right number of asterisk and variable names. So it's complicated in the sense you have to be very careful. Not complicated in the sense that you need a PhD to do it. You just basically just need to take your time, write slow, not make mistakes like I did. And you know, in my defense, I'm teaching at the same time, so you guys can take more of your time to write and not have to talk at the same time. So you guys ready to do this on the midterm then? Can I rely on you guys doing this in the midterm? I mean, it's open notes at least, so you can have that as a reference if you guys remind me to send it to you before. But of course, in the midterm, I'm not just gonna make you give me this code, because I mean, anybody can copy paste. I'm gonna make you do something with the code. So, yep. At least a 2D array. I don't know if I'll give you a 2D array yet. I haven't finished the midterm. I actually didn't finish it, but I have about 80% of it done. But I didn't write any questions from today's topics because I wanted to make sure that I covered everything first. So, yep. You guys are very quiet. I hope you guys are understanding it though. Both the creation and deletion. Which again, deletion is a misleading word. I am confident in my confidence. That sounds like you're very confident about that. So, yay. Okay, so that takes care of one of the 3 topics that we wanted to deal with. So I'm not going to touch this. I'm just going to save this so you guys can have it as a nice little template for. And by the way, in the assignment 5, I guess really the one you're working with is this one. So that's the one that's going to be useful for assignment 5. This one, not really, because you don't have any 3D arrays in assignment 5. But really, 3D arrays is good because you hopefully at that point see the pattern. You know, you can extrapolate this into a 4D array, essentially. You know, once you've seen the pattern of the increase of asterisks and for loops and extra for loop for the delete, and how the parameters go in your for loops. If you really sit down and look at this carefully, you will see that pattern arise, and it's very clear and obvious. And if you just follow that pattern to the dot, then you will make no mistakes. Of course, that's tricky within itself not to make mistakes, even when you're following patterns. Moving on. I actually like that picture. It looks pretty. I will have to print that out. Put it on my office for next summer, because I'm teaching 202 again in the fall, so I'm going to put that on my office. So when people come ask me questions, actually, I don't know. I don't think I'll be able to have office hours. So never mind about that. I'll just put it outside my office. So when they come, I'll just be like, it's outside the office, guys. So, yeah. Okay. Deep versus shallow. Ah, okay. That's a good one. So, let's go back to one-dimensional beings and talk about them for a minute here, okay? So, I don't like how it does this. Okay, let's try that again. There we go. Okay, and then turn this to black and turn this to red. I like these colors like that. Deep versus shallow copy. Before I even tell you what this whole deep and shallow copy is, let me tell you the reason why it's important to know. Okay, suppose that I got myself an array. An array? I just thought about something. Okay. Let me test something really fast. I had a revelation here. Deep versus shallow. Either way, I'll switch over it in a second. CPP. So we know that if we make an array of a one-dimensional array, R, it's new int 10, and we were to see out, for example, R itself or any of the members of R, the actual location of the member, because it's like that, then this should give us all heap addresses, right? Yeah. Whereas if we print out the location of R itself, that would be a stack address, a big number. So with another array, when you do the OG arrays like this, this gives us a stack address as well. But now my question is, if I do this, and I do C in X, and then I do int X, it's OG, and then I print out OG1, am I going to get a stack address or a heap address? Oh, semicolon. Okay. Let's put a 5. I still get a stack address. Okay, interesting. So I thought it might give me a heap address if I did that, but it did not. So either way, what I want to show you guys is if I see out the address of OG itself, OG0 here, and I see out the address of AR0 here, and then I see out the address of just AR itself, I want to show you guys what this gives me here. Hold on, inline to make it easier to see. Okay, so let's look at what each of these are doing, okay? So first we have a array, dynamically allocated array of size 10. AR itself is just a pointer, right? And that pointer is stored in stack, as you can see right here. The $R is giving us the address of R itself. Next, we are basically looking at the array that we just allocated. And I want you to notice that these two lines of code, which are line 6 and 7, are giving me the same address location. So both couting R, which is what it's pointing to, and couting the address of the first element in the array are the same. That confirms what I said, that when you have a pointer, it is indeed pointing to the first element, like literally pointing to the first element. In fact, it has the same address as the first element, as you can see right there. See that? Now, something interesting happens in the other scenario with a statically allocated array. So with a static array, we got OGX, right? The address of OG itself and the address of the first element of OG are the same. So we don't have that level of sort of indirection, I would suppose. So whereas when you're making a dynamically allocated array, the name of the variable that holds the array is held in a different location, because as you can see there, it's just pointing to where the array is. When you're making a statically allocated array, the name of the array itself is the location of the first element, like it actually is, as you can see here. Does that make sense? Yes or no? And then that was also testing the thing about where the location was. Okay, good. So here's the thing, and I'm gonna get rid of this just so that I don't type in enter every single time. Okay, I'll put 10 here. Here's the thing. If I try to copy in either of these scenarios, suppose that I want to make another array, naively. Hopefully they told you this in 135. You shouldn't do, right? Make new OG. You know, I make a new OG array of the same size, of size X. Okay? And then I want to copy OG into new OG. So I go ahead and say new OG gets OG, right? And I compile it. And I get an error saying invalid array assignment, right? Why is that the case? The case of that is because arrays cannot be copied over. It's not something that the language has built in. Fortunately, we get this warning or this error when we compile that. However, let's try to do the same thing. So for now, we'll comment this one out. Let's try to do the same thing with the dynamically allocated array. Well, what am I going to be making here? Another pointer, right? So I'd be like int R2 gets new int 10 to make an array of size 10. And then I'm like R2 gets R, right? Kind of the same thing I'm doing here. Except in this one, it's not going to give you an error. However, this is really bad because just like the one before, you can't just copy arrays. This one, it may seem to be so because you're like a compile, so it must be working, right? But it's not. What you're actually doing here is you're just copying over the pointer. Line 10 is you're just copying over the pointer that is where that basically points to the first element here, and then you're copying it over here. And you may even naively think it worked if you do something like cout, you know. So let's say that R10 or R0 has the value of 22. And then you're like, let me go ahead and see out R0. And you might naively think that this actually worked, because somewhere in here you see a 22. Here it is. Okay, it's, if you want to see it in its own line, you can do that. You might be like, I actually succeeded in copying this. And it turns out that you could actually go through every single element in the array. Like I could print out the 5th element or the 9th element or even the 10th element, I get index 9 of the array. And you might be like, the duplication worked just fine. Okay? But here comes the problem with that. What you did is not a duplication. You didn't copy it over. You merely made the pointer point to the original version of the array. So in picture terms, what you did is, again, if you have the OG array, it's not a circle. Oh my gosh. Are my squares that bad that the thing thinks they're circles? So this is your normal array. Now we know that it doesn't even let me copy that, right? However, with the pointer array, we have R here that is pointing to the first element of the dynamically allocated array. But then we made R2. And I said R2 gets R. All I'm doing is I am copying over basically the address. I'm copying over the address from R into R2. So now R2 is pointing to the same dynamically allocated array. Not just that, but I've actually created a memory leak because I had a dynamically allocated R2. But that's beside the point. So now, if I say something like R2, 3, 0, 1, 2, 3, then I can actually set this to 5. And then this will actually get set to 5. And then I can see out it and I can be like, see out R3. And I'll get a 5 out of that. This will actually print out 5. However, if I say see out R3, so basically this pointer's R3, that is also going to give me a 5. Because I have them both pointing to the same thing. So if I change one of them, the other one changes. Just like when I had a single pointer variable, and I changed that, it would basically change the other one, right? So if I do something like int b, and then I have int ptr, you know, and I set b to be 5, and then I have int ptr, and I do ptr gets the address of b, and then I say ptr gets 6, then if I see out ptr, that's going to give me a 6. But also if I see out b, that's going to give me a 6. Then if I do b gets 10, and then I see out them both again, dog is triggered, then that's actually going to give me both 10, either one, right? Because they're just pointing to the same thing essentially. So what you're doing here by doing this copy is you're not really making a copy. You're just basically making the both points of the same thing. Yes, I'm sure she does. And so this is what is known as a shallow copy, because you're not making really a deep copy per se. You're not making a real copy. You're just making two things point to the same thing, and so you're making a reference to it essentially. You're not making a duplication of it. So this is of course a problem if what you really want to do is make a copy. Like I said, you want to copy your data as a backup per se, so that you can then modify it later on and then have the original one and so on, right? So basically, this shallow copy business doesn't work. Furthermore, as you can see in 135, you weren't able to copy an array. So what if in 135 I told you copy an array? What would you do in that case, even if before you knew about pointers? And the answer is yes. You make a loop, just like you said. So the real copy, or what we know as the deep copy, which is actually making a member-wise copy, you would achieve using a for loop. So let's go ahead and actually do that. So let's do it with both the regular array and the dynamic array. So what we're going to do is, this of course is just a shallow copy and technically a memory leak. So shallow copy and memory leak. Because if you just want a shallow copy, then you don't need to allocate this guy. You know, because you just need a pointer that points to it. So for the deep copy, and I guess since we are gonna deep copy and shallow copy, let's go ahead and actually let's put something into our array. So let's go ahead and make a for loop. I is equal to 0, I is less than 10, I plus plus, and then here let's just go ahead and say I gets I. Okay, just so the array has something. It makes it easier to see what's happening. Okay, and if we want to prove that what it contains, we can let's make a function. Actually, I don't think I've shown you functions with pointers, although hopefully you got how to do them. But we're gonna say void print, and then it's going to take a pointer, and a size. So it's a shallow copy. It's a shallow copy because if R changes, then R2 will change as well. Yes, that is correct. So for int I is equal to 0, I is less than size, I plus plus. And it's probably called shallow copy because it appears on the surface to be a copy, but it's not referenced. I guess. I have the, by the way, I have the definition of the book here. In case you guys were curious. More formally, in a shallow copy, 2 or more pointers of the same type point to the same memory. That is, they point to the same data. That is the official book definition. It is on page 847, but they start talking about it in 845 if you want to see that. And then in the bottom for the deep copy, more formally, in a deep copy, 2 or more pointers of the same type each point to their own copy of the data. As you can see, that's not exactly a very technical definition, but that's what the book says. So, yep. Hopefully, I was very close to the microphone there. Hopefully you guys didn't like destroy your ears or something. So, yeah. PTR is our array in this case. So we're going to do cout PTR I. So a bit of thing to point out here. You can see that when we're passing a pointer, and this is the big thing about a dynamic arrays versus like static arrays. You don't need to pass those weird dimensions when you're passing in like a array with this. You have to pass all the dimensions but the last one and so on. That's disgusting. You just pass a pointer and you can pass a size and you're good to go. Or if you know classes, then you just pass the object of the class and then you deal with everything there as well. So either or. But never ever do the whole array, static array passing where you gotta pass the dimensions. It's just, and I'm talking about for multi-dimensional arrays. For single-dimensional arrays, you know, we all know that you can just do the just square brackets like that, right? But yeah. So this little piece of code will go ahead and print out an array. Yeah. Let's test it really fast. By calling print R on R and 10. Okay, and the rest of the stuff we don't need, but I think it compiles, so we don't need to delete it for now. So, yep, it prints out the array indeed. Cool. All right. So for now, we will add a return 0 here, just so that we don't run into pains with this stuff. Oh, wait, not there, but here. Okay, so let's go ahead and do a deep copy then. As you guys said, it's just a for loop. All we need is a for loop. So first we're gonna make our new pointer, which is R2. We're gonna dynamically allocate it to the same size as the first array, which is 10. And then we are just gonna make a loop of the size of the array, which in this case is 10. And then we're going to do what is known as a member-wise copy. And what that means is basically we take the second array, which is a new one, and we copy into each individual index whatever is contained on the first array's index, equivalent index. That's pretty much it. And so now, if we go ahead and call print array on both of these, so here, let's move this print array to the bottom. And then maybe let's change something inside of them. So let me just change R2 gets the fifth index gets a 99, okay? And then let's print them again. So we can see that it actually only changed R2 and not R1. So you can see, why do we have so many? Oh, I see why. So let's add an end line after each of them. Actually, let's just add that end line to the function itself. Or actually, better yet, when we print this out, let's print it out horizontally. And then add the end line afterwards. That will make it easier to see. There we go. So you can see here, the first two is R and R2 after we did the copying, but then after we go ahead and change R2, you can see that it only changed it in the second one, not the first one. Whereas if I done it the other way with the shallow copy, so I'm coming this line and then coming this line out. Well, I guess both lines technically. Then you can see that in this scenario here with the shallow copy, when we change our R2 to be 99, it actually changed both R and R2. So that was a shallow one. Okay, so that's a shallow copy. So here, let's put, so that I leave this code for you guys, let's put a define. Define should really be on the top. So define shallow. So if not defined shallow, or actually if not defined shallow, if defined shallow. I'm trying to see how I can put this. I have to put a bunch of them. Okay, whatever. Oh, there we go. If defined shallow, then there's that. This one is only for shallow, so else. And if, and then these are also for not defined shallow. So if not defined shallow, and if. Okay. So now if you leave the shallow on, and we run this code. Oh, the declaration. I gotta split the declaration out of that. Good point. Let me just put the declaration up here. I hate the way that I put that logic. Let's just put that there to just avoid just horrifying code. So that is so much better now. If defined shallow, else, which is kind of like deep copy. Okay? Yeah, okay, that looks much nicer. So now, if we go ahead and run this, this is the shallow version, and if you want to run the other version, just comment this out, and then run this again, and now this is the deep copy. Okay, so that way, when I send this to you guys, you have a way of running both easily. Okay, so yeah, that's essentially what deep and shallow do. Of course, it gets a little trickier when you're doing multi-dimensional arrays because you have to allocate. You still have to do the fancy allocation of the array and then do the copying, but frankly, as long as you do the allocation right, the copying it's just a for loop or a nested for loop, but just like any other array. While we're at it, we have the other version here of the array. I suppose this one I'll do as well. So to copy this one yet again, all you really need is just another for loop. So like for int I is equal to 0, I is less than 10, I plus plus, and then you do new OG gets I from the old OG, right? So yet again, just a little for loop there. So run that, and nothing happens. But if we were to call print array on this one, could we do that? I think it might get away with it actually. It should, syntactically it would work, I think. So print new OG 10, and then print OG 10. We'll see. It's expecting a pointer, but technically it's, oh, print array. Sorry. Is it print array or print R? Print R. Yep, it worked. So now we can go ahead and, you know, I don't know what's contained there, but it doesn't matter what is contained. But whatever is contained, we're going to change one of them to be like, not zeros because that might be matching, but 99999, like that. Oh, what? I don't know why I put a C out there. So there you go. Oh, is it printing anything? Oh, it's not, because I have to return 0 here. My bad. Well, it's an array. It's just kind of difficult to see because we never initialized this. It's got a bunch of garbage in it. But even within that garbage, you can see here that we got a 999 in this one, and we got a 0 there, and all the other garbage should match. In fact, so the garbage is lined up. Let's just make it a single digit, and there you go. You can see that the change happens. Okay. So, and before the change, if you want to see it before and after, I can show you that as well. So the only way you can copy statically allocated arrays is with a deep copy, actually. You can't do it with just the equals, as you saw it doesn't compile. Dynamically allocated arrays, you can do shallow or deep. Most of the time, you'll want to do a deep copy. However, I suppose there is a possibility that you may want to do a shallow copy if the task arises for it. So final version, this one, there, it's lined up. Okay, as you can see, here's the change without affecting the top one. Questions about shallow versus deep? Let me know. Otherwise, I will move on to the last topic of the day, which is constructors and destructors. Let me switch over to the iPad. No questions? Okay. In that case, we will move on. The assumption is made that you guys all understood it. I'll switch over to the tablet in a second, or sorry, to the computer. Namespace std and main. And then let's switch over here. Executions to Can you explain the deep copy example again? Yes. Which part in specific do you want me to explain? Like in the code, or like how it works, or what? So basically, with a deep copy, you're making a duplicate of the array, and they're separate duplicates. So you're copying it, and then they're independent of each other. With a shallow copy, you're not making any copying in reality. You're only copying a reference to the thing. So you're only copying the pointer per se, right? And that's, of course, with dynamic allocation, because with static allocation, as you saw, you can't even copy anything at all, because that gives you a compilation error. So again, this is strictly for pointers. With pointers, you're just copying the pointer, basically. You're not copying what the pointer is pointing to, you're just copying the pointer itself. That, of course, is just going to make two things point to the same location, and that's a shallow copy. Deep copy, you're member-wise copying. So you're making two completely separate arrays, and then you're copying each of the independent members of it. So all the index values you're copying manually. And the way you achieve that is with a for loop. So if it's a one-dimensional array, you just need one for loop. If it's a 2D array, you need a nested for loop, and so on. And so basically, what I do is I go ahead and allocate a new array of the same size as the first one. That's it. And then I call a for loop that runs for the number of items I have, so the size. And then I go ahead and just basically individually copy each of the members over by doing this. Now, this is a member-wise copy, and that's good because that's actually copying the data. We're not just making a reference to it. And that's pretty much all there's to it. So hopefully that answers that. Anyways, now we shall do constructors. Yep, you're welcome. No problem. Let me know if there's follow-up stuff. Otherwise, I'll just jump into constructors and destructors. Because this will take us like 10 minutes, and then we'll have basically an extra 20 minutes at the end of class. So we still have time for questions. So you guys know constructors, and I mentioned destructors, and you kind of use a destructor. I found a creative way of using it in the assignment 3, I think it was. And but now I'm going to really show you the power of destructors when it comes to dynamic allocation, because here's the thing. We don't want memory leaks. In fact, not just not want them. You guys don't want them because you get points deducted, right? I don't want them in general because when you have memory leaks in the program, you look unprofessional. Although this goes saying without saying that this doesn't go without saying that sometimes it's extremely difficult to get rid of all memory leaks, and so a certain degree of them are typically accepted in society per se, but in this class it's not, because we're not doing anything that's so hard that it's difficult to get rid of memory leaks. I'm talking about in a real program like a video game or something that's like a massive code base. Some memory leaks are to be expected, unfortunately. It's just too hard to get rid of all of them. Okay, however, you want to avoid them as much as possible, and one of the ways that you can do that is automating the process of allocation and de-allocation of memory, so that you don't have to manually remember these things. And when you're dealing with object-oriented programming, you can actually automate that very easily using your constructor and destructors. And so that's essentially what I'm going to be showing you here. So suppose that we have a class A, okay? And class A has a regular integer, and it has an integer pointer, okay? Now, here's the thing. And I kind of was talking about this the other day when I think yesterday or whenever I was talking about like using the arrow operator. And but I kind of skipped the part where I was allocating and just kind of put it there and not really talked about it, because again, I wanted to really talk about it today. So here's the thing. If I just make a class A like this, and then I try to make an object of this A, so I instantiate an object of A like that, and I go ahead and do A.x, and let's make them all public for now. You can use your getters and setters. You know how to do those. And then I set this to 10. This works fine because this is a regular variable, right? However, will this piece of code work? And of course, this is a pointer, so I have to dereference it. And then set this one also to 10. Is this line of code going to work? As I have it here, assuming that I put my semicolon at the end of the class. Will it compile? Yes, it will compile. But will it work is the real question. What do you guys think? Will this work or will this sec fault? Let's go ahead and put a Twitch poll out. New poll. Will it work or will it sec fault? Work, sec fault. Crash. Duration 1 minute. Start poll. View results. Okay, so here we go. Poll is indeed running right now. And you can see some ongoing results here. We got people voting for, some people say it'll work and some people say it'll sec fault. It seems like people are changing their minds. Now we got a bunch of people saying that it'll work, and we're here to see. We got a lot of people saying it'll sec fault, but we still got people that are confident that it will work. Defined work. Yes, that's how I was going to get to that actually in just a second. True. So I think we can end the poll early. Let's end the poll. So final results. Sec fault is the answer that you guys said. But let's go ahead and run it. Now I get a sec fault. However, this is why I like the question about defining what work really means. You know, and by that I meant basically it's not going to crash and I'm going to be able to store data in there. And it turns out that this is undefined behavior, or what is known as undefined behavior, which means that the C++ compiler or the C++ language rules don't have anything specific to say about this. It's strictly an OS thing. So this piece of code may have worked. It may have. However, it is very highly likely that statistically, yes, I would put my money on it sec faulting. However, it could have worked. Essentially, what is happening is the Y here is a pointer. That pointer is pointing to who knows what, like who knows what. There is no rule that things have to be initialized. More than likely here it's set to 0 by the compiler, or the OS. But like that's more of the OS than the compiler. But that is not something that is in the language documentation. In the language documentation, the description of C++, the rules of C++ that then the compilers follow when they create a compiler, don't say that variables are initialized when they get created. Because of that, it could have anything in there. And if whatever it has in there is a valid memory address by chance, which you have access to, then there is no reason why you wouldn't be able to store a value in there. However, it's also possible that the number there points to an invalid memory address or a memory address that you're forbidden from accessing, in which case you will probably get an error from the operating system, which results in a segmentation fault. So it's undefined, and that's something that it's important to understand, you know, because like syntax errors are the errors in the rules or violation of the rules of the language, right? So those are ones that will not compiler, and they're caught by the compiler, you know. The syntax of a language is the rules of the language. The semantics of a language is the logic of the language, essentially. So what you're trying to say. So syntax errors can be caught by a compiler, and the C++ is very specific about what the syntax should be so that you can catch syntax errors. This is a semantics error. Therefore, it's not caught by the compiler because it's just a logical error. And the fact that it's a logical error has to do with what you're trying to say. But maybe this is what you were trying to say. Maybe you wanted to do this weird thing. Maybe that was what you intended to say. In which case, it's technically not a semantic error. It's because that's what you wanted to do. And so it's very important. And I will try to revisit once in a while the idea of undefined behavior, because it's an important concept to understand that the compiler, you know, is only following the rules set forth by the C++ documentation, the standard. You know, when you say C++ 11 or 17 or 98, those are the standards that they came up with. But those standards are just rules. The compiler can add in their own set of rules or own set of requirements, because again, it's just, you know, it's like I speak my own version of English. You know, there is of course a dictionary and there's grammar rules in English that I have to follow, but within those grammar rules I can say whatever I want, you know, free speech or whatever. So I can say something that is grammatically correct, but makes no sense. Like, I eat walls. That's correct grammatically, but it doesn't make sense to eat a wall, because, like, what? You're going to die probably if you eat a wall, assuming you can actually chew it. So that is kind of the whole idea between a compiler is just going to look at the rules of English per se. If you're making an English compiler, it's going to look at the rules of English, and then it can add its own extra set of rules and so on. And the operating system on the side of hands is going to just interpret what it gets and just run it. At that point, he doesn't care what the C++ rules are. He just cares about what he got as machine code. So anyways, it's a little bit of an aside, but it's very important that you understand that. And I will check on the final exam about the undefined behaviors. So yes. Okay, so going back to this, how do we fix this problem? Well, one of the ways that we can do it is we can dynamically allocate the memory so that it points to something valid, or we can make it point even to X if we want it, or whatever. So in this case, let's go ahead and dynamically allocate it. So the easiest way to do this right now would be to just say AY gets new int, right? And then I can then go ahead and say asterisk A.Y gets, let's do a different number than 10. And I can also see out it, right? I can see out AX. In fact, let's write a function here that prints everything here. So now we don't have to call it multiple times the print. And that's going to see out X, and then a space, and then it's going to see out Y. It's contents, like that, and then an end line. Right? So now we can just call out print here. Like that. So we get 10 and 9. Okay? But now, because this was dynamically allocated, we have to remember to delete it. Because right now, if I run background on my output here, you will find that there's a memory leak. 4 bytes lost in 1 block, right? So how do I fix the memory leak? I can do AY. I can do delete. I can call delete on A.Y. And then maybe, since I'm a good programmer, I'll do A.Y gets null. And then hopefully here I have an if statement, which I don't, but I would, checking to make sure that Y is not null before trying to print it so that this doesn't crash, right? But I'm not going to put it right now. So if I compile this again and run background on it, I fix my memory leak. Now here's the thing. Suppose that I got to make a bunch of A's. So let's make a second one for now. So another A. So let's call it A2. And then A2 needs a Y as well. So then we would do A2.Y gets new int. And then we can go ahead and do AY gets, I don't know, 8 in this case. And then we're not even going to initialize that one because YOLO. And we can call print on A2. And then if we forget to deallocate that one, you know, this will run, assuming I don't make typos, but it has a memory leak as well, or it has an error in this case because oh, and then the segmentation faltered. Oh gosh, what happened? What happened indeed is a good question actually. Why did this segmentation fall at the end like that? A2.y new integer 8y. Oh, I see why. Well, actually, I don't. No, I do see why. Yeah, it's because of this line of code. I'm actually modifying the first A, which I went ahead and set to null. So yeah, and so basically I am setting address 0 to be 8. So yeah. So anyways. Now I see my memory leak. So I'm actually kind of glad that I made that mistake because yes, now I can call delete on the second Y as well and set it to null. But you can see how, I mean, this was not scripted. This actually happened for real. Like I actually made that mistake, and that is actually one of the reasons why what I'm about to show you is a better way of doing this. Because here's the thing, I accidentally, you know, I had to at some point delete my variable from here to avoid a memory leak. So I could either procrastinate and do it at the end or do it immediately after I don't use it. But either way, If I happen to accidentally access it, I segfault, right? So also, having to keep track of this allocation and deletion can be a pain, like a headache. And so if I don't want to do that, you know, there's another way. There's a better way to doing this. What is this thing? Oh, it did? I didn't even look at that. Oh, yeah, it did have a bunch of errors. Conditional jump depends on initialized value. Oh, the errors are probably related to this line of code. The printing, because I don't set the printing to something. So I have to do like a2.x gets 10 or something. So that it's initialized. It's complaining that I'm trying to print something that I never initialized, which is true. I just didn't have to because I was lazy. So now it fixes that. So it's just because 10 had some garbage in it. And that's, again, you know, it compiled and worked just fine if that's what I wanted to do, but technically it's dangerous because it's not initialized. So that error is not, it is bad, actually. It is bad because you're printing something you never initialized, but it's not related to memory leaks in this case, okay? So, but anyways, as you can see, that's I fixed that. But so this is bad because I have to keep track of all these deletes and news of all the variables inside the class. And the whole idea of the class is to not have to avoid doing all this stuff, to automate it, right? And so the other place that you can do your allocations to just save yourself a headache is in the constructor. So your constructor, remember, when does that constructor run? When the object is basically entering the scope, when you're allocating the object. When you first see the object, when the object gets created, which is when it enters the scope, the constructor runs. The constructor is supposed to initialize things and so on. But another thing that can be very useful for a constructor is to allocate memory. So let's go ahead and initialize the constructor always to 10 for the x value. That way we can avoid this line of code. Okay? Furthermore, the constructor can also dynamically allocate memory for us. So right now, everything's still good. But check it out. I can go ahead and say y gets new int in here. And so now, automatically, when the object gets created, which is happening when I do this line of code here, automatically at that point, it will go ahead and allocate y. So I don't need to worry about manually allocating it. So that takes care of this line of code for both. So that's convenient. I don't have to remember to allocate memory. It will do it for me. Let's run it again. 0 errors, 0 memory leaks. Furthermore, for the allocation, I can take the same approach. I can create a destructor, which again is with the tilde in front of the name of the class. And the destructor runs when the object leaves the scope. What that means in layman's words is when the object is no longer used at all, or the program ends and the object is getting sort of kicked out of memory, or if you have an object inside a function and that function ends and you're no longer going to use that ever again, which again is leaving the scope, that is when the destructor runs. And that is where you can call your de-allocations, because that means you're never going to use it again. And this for sure means you're never going to use it again. So that's good for us because that's when we really want to call it, and we don't really have to call it beforehand. So for that, we can go ahead and just call our delete y there, and not have to do it before. Why? Yeah, there we go. Color coding. So now, and I guess technically you could do this. You can set y equal to null here, but again, this is running at a point where you're never going to be able to access it again, so you don't need to. But I guess if it makes you feel better, you can do that. So that gets rid of these lines of code. As you can see, no memory leaks, no errors. And now, we don't, I mean, yes, we could have these if we want to access it. We could do that somewhere else. But the point is, we no longer need to worry about allocation and de-allocation when we're using objects. And by the way, that is why in the past when you were using vectors, strings, or any other sort of libraries that were using dynamic stuff, you never had to worry about allocating and de-allocating things. It was done behind the scenes for you in the constructor and destructor more than likely. So big powerful thing. If you really hate new and delete or malloc and free, you can chuck all that in the constructor and destructor and never have to see it behind the scenes. Of course, technically the other way well, no, that's it. That's all I want to say about that actually. So the last thing I want to show you though, unless you have any other questions, is suppose that we wanted to make a dynamic object of A. Okay, so suppose that I wanted to make A2, or let's make an A3, But A3 is not any A3. It's a pointer of A3. So we're going to dynamically allocate it by saying new int. Okay? So, ooh, what? No, not new int, sorry, new A. In this scenario here, I went ahead and created an object of 8 class, but it's a pointer. So this is also the cool thing. This will also allocate my Y behind the scenes. So otherwise, I would have had to do some A3 arrow Y gets new int, right? I don't have to do that anymore. I can merely access things. If I want to see out that value, or if I want to set it to something, I can do 7. And I can call print on A3. So A3 print like that. Because again, I don't want to have to use the other nasty method, but if you really wanted to see it, I could show it to you. At least I'll show it to you for this one, just as a refresher. As you, oh snap, memory leaks. Oh, well, I have to delete the object A3 that I made. So there you go. No errors, no leaks. For the string assignment, do we do, well, do we do word new car 0? Why would you do car 0? Car 0, when you're allocating an array, a dynamic array, so when I'm making an array of these things, you know, if I'm making like A equals, you know, suppose that A is, or X, Z is an integer, and you're making an array of them, enter your pointer, you're putting a size in here, right? Some size. Don't put 0. Why would you make it 0? That's basically means that you're making no size, which by the way, this is weird, and I guess it's a good point to talk about it. If you call malloc, or if you call new on something of size 0, actually with new I'm not sure, but with malloc, it would always give it to you at least 4, or sorry, either 4 bytes or at least 1. No, I think it's at least 1 byte. It'll give you at least 1 byte of memory. So if you try to allocate 0 bytes of memory, and then you run your code and it works, and you're like, whoa, that's not what's happening. What's happening is you still get 1 byte back, and then you're just going out of bounds, but you're not crashing because you're getting lucky. So anyways, don't do anything with 0 in the brackets of new, because it makes no sense. I guess I'm not really sure how to dynamically allocate an array of size that I don't know yet. Just like this. So let's say let's add an array to this thing. Let's make an array of doubles this time, because we use a lot of integers. So here, array of strings. Why not, since this thing is a string, right? So we'll call this a string str. And we'll make it a pointer. And so if you want to allocate an array, you know, we'll make this a parameter here, a optional parameter. We can say int s gets by default 5, okay? And if you want to make it by default 5, and then you want to allocate it here, you can say str gets new string s. And so now it's going to make it the size that you want. If you pass it a specific size, it'll make it that size. If not, by default, it'll make it of size 5. So just pick that. If you wanted to make your default 0, then you might have to add an if statement saying do not even allocate it or something. But that's kind of dangerous. You always want to make it a size of something. Because think about it, a string, even the empty string, always contains 1 character in it. And that's the null character. The null character is represented by \0. Okay? So suppose that we do that actually. So we say s1 is that. So then we can say if s is equal to 1, or if s is not equal to 1 actually, then we will do that. Else str gets new string 1. No, let's change that. We can say if s is greater than 0, we do this. Otherwise, if it's 0 or less, we still do 1. Yeah. But we fill it in with just an empty. Either an empty string like that. Well, it's an array of strings. So then we'll go ahead and fill out spot 0 with the empty string or something. I don't know. Whatever you're trying to do, doesn't matter. But the point is that you will want to pass in the variable here, which is the size. And if it's a default parameter, make sure it's not 0 so you don't accidentally switch things to 0 by checking that here. And if it is 0, then either set it to a size of 1 or something, or don't even set anything at all. But that will cause issues with your de-allocation because Destructor, you want to make sure you delete it. And if you're deleting it, you want to know what size it is, right? So actually now we also need to keep that S here so we know the size so we can delete it accordingly. Actually, right now, if we always guarantee that it's a certain size, then we can do delete str, as long as we always know that it's a specific size. So, like that. Let's get rid of that. I don't like that. There we go. So for the string and potato, when I do the assignment operator overloading, how do I even work with the right set as an object? I guess that's what I'm really confused about. You're parsing it. That's the string and potato. I'm assuming that's the input text file, right? You have to parse that in. So you have to tokenize it, kind of like with the Twitter stuff, and then you parse that in. Assuming that that's what you're talking about. Also, you need to review your operator overloading stuff. More questions? Yes, that will help the most, frankly. Are there any questions about, I guess first about the constructor and destructor for using new and delete? Gotta make sure you guys understand this before we try anything with assignment 8. We want to make sure that we get down the whole constructor, because I mean this is strictly optional, but it makes your life so much easier. So you want to use the system of using all your allocation and de-allocation to happen in the constructor and destructors. You know, it just makes your code much easier to avoid memory leaks. Sometimes you're forced not to do it this way. Sometimes, if that is the case, then of course, you know, deal with it. But ideally, you want it to be like this. On the recent assignment, how were you able to redefine the doc_d class without running into a class redefinition issue? That's a very specific error that you're talking about. I'd have to see what you did. But I don't think I redefined the doc_d class at all. Nope. I merely, I mean, I think there was like an animal class that we then inherited and made a doc_t class, but you're never redefining it. So what you're doing, what you probably did is you probably try to put like two doc_t classes, you know, that are both called doc_t, and that would cause that error. So I did not run into no such error. So you'd have to kind of look at the line of code where that error is coming up, and then see, you probably have something. That's like me saying class A here. If I have a class A here somewhere like this, I would get that error basically. See? Redefinition of class A. But then again, why would you be doing this in the first place? That sounds like a bad idea. Like, why? So you probably did something like that by accident. So check your code and see. For assignment 8, would using the constructor to allocate and create the word be fine? I think so. Actually, when you create a string initially, you may not get something in it passed in. So you can try as long as you actually have the data to create it with. Otherwise, you can create it, but just make sure you keep the size somewhere so that you can switch that around. So otherwise, you won't be able to delete it. Also, in assignment 8, it's use a file. Where do we find the file at? I mean, used a file as input, but if you want the text of the file, it's on the PDF. That's just the text that I give you in the PDF. Just copy and paste that into a file, basically. Or type it in or whatever. What I'm saying is you're using a file as input per se. I don't think it's I think it's file streams. It's not Linux Resurrection, or even if it's either one, you're still feeding it a file. So yes, this time I didn't take the effort of copy pasting the PDF contents into a separate file. I assumed you guys could copy paste. Whoa, I got like 4 messages at once. Yeah, it was defined previously and later you redefined the print, but probably made a mistake somewhere. Yes, so redefining the print is just one function. So that's full function overriding. But you must have at some point put the word class and then the name of the class, because that's what would cause the error. So somewhere in there you have a typo like that. Typically, it tells you the line of code. Like it told me a line of code to check out here. You can see it was like, go to line 25 or line 4. You know, those are the 2 times that it appeared. So that's kind of what you kind of wanted to jump and see, and see if that kind of gives you a hint. Maybe not exactly that line, but around that line. So you want to check that out. As for assignment 8, that's text. What you're looking at is text. You're looking at a file that's text. And then you're processing that into the program. Okay, so like imagine that I had a program that I can feed it in a message that says string equals a. That doesn't mean I have to upperload the assignment operator. That just means that I am going to parse this in, and I'm going to read the word string and know that that's a string. Then I'm going to see the equal sign and know that I have to assign into the string I'm going to make whatever is next, and then I see the potato. So that's parsing. That's not necessarily that you're typing in that as code. It's parsing. It's a different thing. It's like, think about assignment 1. You have tokens, which are words that you're reading into the assignment, and then you parse with the commas, right? You use the commas as a way to separate different tokens, right? So that each one goes to the tweet and the other one goes to the date of the tweet, I think, and then whether it's a retweet or not. So that is parsing that you're talking about. It's different than actually writing the code. So yes, I would have to, maybe I can find an example by pulling up the assignment. Give me 1 second to pull up the assignment. Assignment, it's 8 actually, right? Oh, actually, well, yeah, no, here it clearly says you have to overload the operator, so you have to do that as well, apparently. Yep. Make sure you overload the assignment operator. That just makes your life easier. But either way, if you look in the sample input category, let me see if I can show that on the video. Like, frankly, you can overload as many operators as you want. That will make your life like even easier. But what I'm talking about is this, okay? This is what your input would look like, as in input, as in the input file per se, okay? This is, or where if you were typing it in, this is what you would look at. So you have to parse these messages and then call the right operations. So essentially, you get the word banana, then you have a space, so you can use the space to separate tokens. Essentially, I think I say that somewhere. I will always put spaces between, so that way you can use like cin even potentially. Although you don't have you have to do your own cin modifications to be able to get that working. But then you can use the space to separate. Then you can read this into the operator. Then you can use the space and so on. So you can continue doing that. And again, that is parsing. It's not, you're not typing this into the program, because otherwise, like, you actually couldn't achieve it unless you used you couldn't achieve it in general. Yeah, because that's what JP was saying. Well, he didn't say, he sent me a message on Discord. Basically, you can't change the operator precedence in C++. Like, you're giving an operator precedence and you got to stick with it. So if you want to override that, you wouldn't be able to. But this, again, is parsing input from a file, so you can do whatever you want as input, right? So hopefully that makes sense. So yes, you are correct. You are correct indeed. So in what you said, that you want to be able to write something like this in the program. Yes, you want to be able to do that. However, this is in the program. So yes, this you want it to work if you were coding it as actual code, whereas this one is actually just input from a text file, which is different. So you are absolutely correct in that. I apologize if I got you confused with that. Here's my dog as an apology to you. In dynamic arrays, are we able to add to the array size when we reach the array size limit, or does the array size have to be static? That's dangerous to trying to resize something. Typically, what you have to do is you have to make a new array, and that's just bigger, and then copy the contents of the old one, and then you have extra space. There is no way to resize it. If you think about vectors, because vectors you're able to do that, right? Vectors you can keep adding forever. How do you think vectors are implemented? Vectors are actually implemented using just arrays, and then the resizing happens behind the scenes. So yeah, even the people that made vectors, which are pretty smart people, can't figure out an easy way of resizing it. You can do some pointer magic and kind of get away with it, but I would highly discourage it because it's really bad. So yes, yeah, she has big ears indeed. Other questions? Let me look at the assignment and see if there's anything I want to point out actually while I'm at it. So it says here you're using Linux redirection for it. So you don't even have to use file streams. You can use Linux, which means you could, if you're testing your program, what I recommend when you do this is you just do one thing at a time, like do addition and do subtraction, and then that's it. Then you can test that in by typing it in. So I guess the first thing you want to do is be able to parse tokens in. That's not too bad. There's getLine. There's cin is not gonna really do it for you because you can't use the string class, and that's kind of reading into a string already. So unless you overload it, but even when you overload it, you gotta figure out. My suggestion to you to read in the input is to either use getLine, but if it's not a string class function, which I don't think it is, or what I think is even easier is just to use a loop of cars, and then just reading each car until you get to a space. The other thing is to detect the line feed, and that's \n. You can use that to detect a line feed or a space. Okay, I will always separate things by space because otherwise the parsing would be like 10 times more difficult, and that'd be more of a compiler problem, CS460, than a CS202 problem. So yes, you will learn about doing some really cool parsing stuff when you like move on into the upper level classes, like 326 and compilers especially. getLine is part of the string header. Oh, well, there you go then. And you have to use for loops. Let me see what I used in my solution. My solution is not showing, right? Okay. If you are curious, 239 lines of code. And then, yeah, I used the for loop. I used a function called getCar as well. And I used a function called peek. So getCar and peek. However, don't I have a solution to that piece of assignment on Canvas? I seem to recall that as a thing. I think I got frustrated and I just posted a part of a solution for that. So check Canvas actually, because I think I might have a solution for the reading input part. I'm like 80% sure about that. Now I'm gonna open up Canvas and see. Yeah, sample code reading text. Yeah, so I have a solution on Canvas to your input, reading, and output. It's literally here. So just check that part out actually for that, because I feel like a lot of people basically struggled with that part when I gave this out in the spring of last year. So yeah. I went ahead and actually published that piece of it. So I would check that out. And you can use that code because I posted it. You do, but my confusion still comes with how to work with the right side of the assignment operator to get started on the assignment. Well, in the book or on the video, I have an example of overloading assignment operator. That one is not necessarily hard. You have to make a member-wise copy, okay? So deep copy. You're making a deep copy per se, and that's pretty much it. Just make a deep copy of the right hand side into the left hand side with a for loop. That's like literally all I have for that. I'm gonna put it in Notepad so I can show that piece of code. That's like a hint of an example of it, you know. It's kind of like that, but it really depends on how you're implementing this. But like, it's just a for loop essentially. So, all right then, I shall head out because I'm gonna go eat. But if you have more questions, then let me know on Discord, and I will try to help out. All right. So hope you guys have a good day. And I will see you tomorrow. So we try to bring questions if you have questions about the midterm. Bring them in ready tomorrow to ask. If you want me to cover something again in detail, not in very detail, but you know, within a certain extent, I have enough time to cover something. I'll try to do a mini review if people have questions. If you don't, then I'll just tell you what the test has in it, and then I'll call it a day on that piece of the review. We'll still learn material, but I want to dedicate like half an hour or something. So bring questions for that. Okay. So I'll see you guys then. Bye.